All right, so let's add another piece to all this. Sometimes when we're looking at data, just like what we've got here on the left from our spring and weight example, that we also want to take a look at things visually. That sometimes the visual representation of what we're analyzing is a lot easier to understand than just a list of numbers. And so what we want to talk about next is how do we go from the equation to the table, but then the table to the actual graph. All right, so here's an example. And notice the instructions have just changed a little bit. Instead of filling in the table for this linear function or linear equation, they're asking us to graph it. All right, so what we want to do is basically go through the same process we did before, except we're going to just add one more step on the end. So first thing we're going to do is we're going to add in some numbers for our input for x. And again, these can be whatever you want them to be, although once again, I'd pick at least 3 and pick some positives and some negatives. Let's just keep it small. Let's just go with 2. All right, so I input 2. I do my calculations, just like our function machine does. 3 times 2 plus 1, we're just inputting in for x. We would get 6 plus 1, which gives us an output of 7. Let's do 0. If I input a 0, 3 times 0 plus 1 equals 0 plus 1, which is just 1. And of course, let's do some negatives. Let's do negative 3. 3 times negative 3 plus 1 equals negative 9 plus 1, which equals negative 8. Okay, once again, we're just picking input numbers at random, just making sure we have a variety. All right, so now basically all we're doing is we're just treating our input and output numbers as xy coordinates. 2 is our input number, or our value for x. 7 is our output number, and that's going to serve as our coordinate for y. And so in this case, we're just graphing the point 2, 7. So 2, 7 would go right there. The next one, we just do the same thing, 0, 1. So across to 0, up to 1. And then negative 3, negative 8. So across to negative 3, down to negative 8. And here, we're actually going to start to see why we call these linear functions. It's because the information that we're looking at when graphed, if we were to fill in all the other pieces of data that we didn't do on our table, we would find that all the data forms a straight line. Okay, so that's why we call these equations linear equations, is because the data that we get will always follow this visual pattern of falling in a straight line. All right? Okay, let's do one more like this, but we're going to add one little twist to it. Take a look at this one. We would like to graph the linear equation y minus 3x equals negative 7. Now, take a look and notice how this is a little bit different from the rest. And think to yourself, well, what do you notice? Well, to me, what I notice is something we did back in chapter 1, which is that this is not set up to spit out y as an answer. All the other ones, like the one we just did, said y equals 3x plus 1. The other one said y equals something. So these were all set up to spit y out as the answer. But this one isn't. This one says y minus 3x equals negative 7. It's not set up to spit out our y output number. Okay, well, what we want to do here is something we did back in chapter 1, is we want to rearrange this equation so that it's solved for y. We want to get y by itself, just like in the last example. So think about what you would do here. How would you get y by itself? Now, if you are recalling your skills from chapter 1, what you would do here is you'd basically get rid of the minus 3x by adding 3x. Okay, so what we now get is y by itself equals positive 3x minus 7. Okay, and now this equation is set up to be used with our input-output table. I can now pick numbers like, let's say, 1. I can plug them in. So 3 times 1 minus 7, which is 3 minus 7, which is negative 4, and it automatically spits out my value for y. Okay, so sometimes this will be a necessary step. The equations that we get aren't always set up to start working with immediately. So sometimes we have to solve for y first, rearrange the equation, so that then we can jump to the table and this equation spits out the answers that we're looking for. Okay, again, let's pick some more numbers. Let's do negative 1. So 3 times negative 1 plus, or I'm sorry, messed up there, minus 7 equals 3 times negative 1 is negative 3. Negative 3 minus 7, that's negative 10. And one more. We got a negative, positive. Let's just do a slightly bigger number. Let's do 4. So 3 times 4 minus 7 equals 12 minus 7 equals 5. Okay, so now, just like the last example, I treat my input number for x and my output number for y as xy coordinate pairs, and I just graph each one. 1, negative 4 would be right here. Negative 1, negative 10 is a little bit off my graph, but it would be approximately right there. And 4, 5 would go here. Now, this is the other reason why I'm asking you guys to do at least 3 input-output calculations, is because that way we can tell if we're doing anything wrong. Okay, if we were only to do 2, we might not realize we've made a mistake and find that we didn't do one of the calculations right. But by doing 3 of them, and knowing that all 3 should form a nice straight line, we've got a better chance of, how do I say this, a better chance of being correct on all 3. It would be a lot easier to spot if 2 of these lined up and one of them did it. We know we have to go back and fix something. Okay, so make sure your data points all fall in a straight line. Once again, this is why we call them linear equations.